Thanks, Oliver. So I think we can all agree that for efficient parameter inference from cosmology, we need accurate and efficient forward modeling. And also one of the most powerful and most accurate forward models are embodied simulations. They are, however, not very efficient, as we also know, usually requiring thousands of steps until they converge to the scales we want to resolve. Like a couple of months ago, Florian, who is also here in the audience, and Oliver, we introduced Bullfrog for classical simulations that greatly rectifies the shortcoming of the standard symplectic integrator, usually only requiring a couple of time steps to get good performance. And today I will also talk about actually applying Bullfrog to a semi-classical system where we actually observe a similar performance boost with Bullfrog. So specifically, I will talk about Schrödinger-Poisson. And for those who don't know much about Schrödinger-Poisson, you can essentially do two things, I would say, with Schrödinger-Poisson. One is either you take h bar over m seriously, which means you might have a particle dark matter candidate into mind, and then you fix it according to that mass. Or this is more like what I'm referring to today mostly, is treat h bar as a free parameter of your approach, which acts it acts as a resolution scale parameter in the sense that h bar, a small h bar, gives you more information basically on nonlinear scale. So in some sense, you can get coarse-grained approximations to Vlasov-Poisson by doing Schrödinger-Poisson. And this whole framework is kind of based on this kind of correspondence between Vlasov-Poisson and Schrödinger-Poisson in the limit h bar going to 0. Just a very brief motivation why I don't want to exchange Vlasov-Poisson. Vlasov-Poisson is a good description, but should be motivated anyway, I think. So after decades of research, we still don't know what dark matter actually is. So if we believe that it's a particle, fundamental particle, then we would also expect that it exhibits certain quantum effects on very small scales. Or you can also consider like a motivation in a classical sense, where you have just an ensemble of classical particles, which then would be described by the Liouville equation. Either way, you can, of course, start assuming that on large scales, like on cosmological scales, that these microscopic particle effects should not have an important role. So that motivates, to a large extent, a fluid description. That is, in our case, also based on the Vlasov-Poisson equations, where dark matter distribution is thought to be a continuous distribution function and solved by the very Vlasov-Poisson equation. Now, on top of that, we also know from the CMB observations that dark matter is initially very cold. And that actually comes with a simplification to some extent in the phase space, namely that dark matter is confined on an infinitesimally thin phase space sheet, as I also show here on the right figure. So all particles are just located on this submanifold. And also, basically due to the coldness of dark matter, initial coldness, it also means that we can actually solve Vlasov-Poisson along the fluid characteristics and that basically boils down to Newtonian type equation of motions. So it's again kind of a simplification of the problem that we can then also use these equations. And finally, there's of course kind of embodied approximation where you say, okay, let's core sample the phase space distribution function by using like a set of discrete particles, as shown here on the right, like just by 2 particles, which of course is very bad approximation. But let's just dump a few more million particles, then you have like a zoom in a classical embodied simulation. And of course, provided that you have enough resolution, you have added enough particles, you should get a very good approximation of the continuous distribution tracing back to Vlasov-Poisson. Just quick recap, because it's also meant as a motivation for Bullfrog and so on. Classical integration of Hamiltonian equation of motion is of course essential for example, an embodied approach. And one way to do that is you basically you consider like a second order leapfrog scheme as shown here. And in practice, this scheme is second order accurate, or like after shell crossing slightly less. But I will not go too much today into the details of the symplectic standard integrator. Specifically, I will not mention too much about one of the most limiting factors, which is the force calculation. So let's just blind it out for today, because today I want to instead discuss what can we do to actually improve the temporal domain of the time integration part. Yeah? So very important features of the standard integrator is that it is second order accurate. Otherwise, it would be not very good, of course. Yeah. And it's also symplectic, which means or implies that certain stability constraints relative to like the energy conservation and so on. But it does not have like built-in physics. It's kind of an agnostic scheme. It basically follows certain recipes to stabilize certain quantities, like, for example, the total energy and so on. So D-time integrators has been recently introduced by Florian and Oliver, and that's a very interesting framework. Also, really very important for my further development the last few years as well, because it actually gives you direct access to implement insights from analytical considerations, and I find it's always very helpful. And so, I mean, it looks almost the same, we might say, but there are like huge differences between these integrator schemes. First of all, the drifts are like linear in the structure growth D. So it's a different linear operation at this level already. But even more crucially is the kick update, because now the velocity is not defined in terms of a canonical formulation, but it's actually defined by the rate of change with respect to the current position of your particles, and of course relative to the time variable used in this system. And as I show, you can actually incorporate certain insights from perturbation theory, for example, this way. And of course, it's also highly performant because of that, with a few time steps, especially on very large scales. So just quickly flagging up, this class does not only contain bullfrog, which I will mostly talk about today, of course, but also quite a popular choices of fast PM, and also PowerFrog that has been also introduced like about a year ago, I'd say. Yeah. So, but let's quickly focus a bit more on Bullfrog. So, where does the performance boost come from Bullfrog? So, when you look on like this kind of sketch, what an integrator has to do, you see due to linearity of your integrator, you do like a linear step here. And if your step size is large, you will drift particles to like a position that is slightly off-grid relative to like the true solution. Supposedly, you know that, yeah. Now, supposedly, at least if you were in the regime before shell crossing, we can compute exactly what happens after performing a linear drift. We can basically look what is the acceleration or the force field at this misplaced position and calculate based on that, essentially by perturbation theory, what the actually the chain of commands basically dictate where the particles will end up. And by doing so, we can also then use these constraints basically to fix these unknown parameters in the integrator. And these are really just like time-dependent functions that you can determine once and for all, and then you're good to go. So there's no further input required in this integrator scheme, as opposed to Coda, for example, which works a bit differently. Yeah? So just quickly, like what the performance looks like in comparison to like a standard symplectic integrator with 10 steps and 1,000 steps. And you can see already on the depicted scales that already 10 bullfrog steps actually gives a very good picture of the situation. And something that also, I mean, Florian pointed out yesterday, we should emphasize, yeah, is bullfrog is highly performant on large scales, probably as good as it gets. But on small scales, you don't really do any mistake either, because it actually is still a highly performant scheme. So it's kind of surprising, because I mean, we know that 12PT is not really meaningful on small scales. But as long as your integrator is consistent implemented, it seems to have quite a minuscule impact, basically, also even on very low small scales, which we find very interesting. So just a bit more qualitative results. I will just flag it up quickly because I want to talk now a bit more about also the Schrödinger-Poisson shortly. If you have questions, results, I can of course answer later on. Just what I find very interesting with both Bullfrog and FastPM actually is that you have this kind of monotonic convergence in a number of time steps if you want to resolve a certain scale, basically, yeah, which is something that we observed in all our experiments, basically. This is a very nice trend to have. So now let's come to Schrödinger-Poisson. So instead of floods of Poisson, one could seek also solutions to Schrödinger-Poisson. So there's a long history actually where this comes from, probably tracing back to Madelung, who did like the first steps. And actually today we have also like Norbert Mauser, who actually was involved in this kind of limiting derivation, not the derivation limited, but in basically computing this limiting process and basically deriving from Schrödinger-Poisson the floods of Poisson equations. And so this is essentially one of the foundations why also then Vitrov and Kaiser motivated such a description for cosmology later on. And so one idea is that we have with the Schrödinger equation, we have now a complex scalar field. And by essentially evolving like the modulus of the wave function and the phase, we basically encode both the density and the velocity by this complex wave function. And then, as I said earlier before, we basically can, in principle, capture also wave-like dark matter phenomena with this approach. And in principle, also particle self-interactions could be included, of course. And but what I find actually very interesting as well is just basically interpret h bar as a free parameter that basically acts like as a resolution swap, basically. Yeah? So you're basically unlocking more and more nonlinear information on small scales when you decrease h bar. So just briefly, time integrating Schrödinger-Poisson. I mean, you can also write down a leapfrog scheme for this, of course, and in practice, the integrator is about as performant as in the classical case. So it's a second order accurate scheme. After shell crossing, it's 1.5 because of shell crossing effects. I can also talk about that if you want later on. It's a bit technical. But also it has no really insights from analytics. It's really an agnostic scheme, basically also symplectic, and doesn't really doesn't scale well at all when you reduce the number of time steps. So basically, based on the avenues with the classical Bullfrog integrator, basically I looked also now on a similar D-time integrator scheme within the Schrödinger-Poisson system. So there are some similarities with the old one as well, and also, I mean, I can establish not just Bullfrog but also FastPM integrator in this scheme. And yeah, so it's in principle straightforward to implement once the stepper is known. This is a good message, yeah, but it took me quite some time to actually deduct this at the end. But yeah, now it seems to work. Okay, so just quickly some results. Like high precision tests in one space dimension. So when you have essentially like a lot of time steps and you want to first see if like the new integrators, which are here like the green and the red scheme, asymptote to like the classical solution, which is just like a classical embodied simulation essentially. Yeah? And you see also, of course, that the smoothed standard Schrödinger approach also converges in that limit to the classical solution as expected. However, now if you reduce the number of time steps, you see the unfortunate feature of the standard Schrödinger approach that gets the caustics completely wrong. And so it doesn't really scale well when you reduce the number of time steps. Well, the other integrators, the fast integrators, they actually get the caustic shapes right. Okay, let's just quickly going through this, like numerical tests of convergence. Also here, just quickly, I find it quite nice to depict basically both the classical solutions and the semi-classical in one figure. So the lines are essentially a selection of classical trajectories from an embodied code, whereas the color is like the density based on the wave function. Yeah? So you get like quite a unified, nice picture between the two approaches, which I find always quite interesting because when you look at the equations, they are completely different. So you might think the solution should be also different, but not really. Yeah? It's quite similar. Now, finally, some results in 2D. So just comparing against like a classical bullfrog here with just 10 time steps. This is a 2-dimensional test. So I'm doing random initial conditions here. It's still testing phase right now. And I'm using like a power spectrum that is basically inspired by Einstein-Hue shape. And you see here on the right-hand side, like the semi-classical solution. So we see basically the large networks of structures look very similar. But then you see also some interference patterns. But if you now apply some smoothing, you basically get rid of these on large scales. You get only some residual smoothing effects here on very small scales. You can now, of course, now play the game and reduce H bar, and then you will get rid of also these smoothing effects, and so on and so on. But then, of course, it becomes more costly and so on. Final test here. So the implementation of the semi-classical bullfrog actually is pretty straightforward. There's just FFTs in between, whereas the classical one is a bit more elaborative, as many people of you know. So I also tested really like a global spatial refinement scheme, for example. And what I find very interesting is that the overload computational speed is actually faster if I compare it with a Nuft force computation. And also the memory requirement is lower. And this is just a 2-dimensional test in 3D. The difference should be even larger. So, which brings me to my conclusions. So I think PT, perturbation theory inspired integrators are definitely very important because they can alleviate like a bottleneck in the computation of like fast forward modeling with decent accuracy. And I think I will stop here. And you see also the last points I mentioned here. Yeah. Thank you.